Okay, class, in this lesson, we are going to learn to compute interest on an account that compounds continuously. So let's go ahead and get started. All right, so if you were to deposit $1,000 at 100% interest rate, what would be the ending balance if it were compounded daily for 1 year? Or if it were compounded every hour for 1 year? Or compounded every minute for 1 year, or every second for 1 year? Well, we already know how to calculate this because we have the compound interest formula, right? But the question is, how would you calculate it if it were compounded continuously for 1 year? So to understand this, we need to go back to some fundamentals, and this is where we kind of begin with an understanding of calculus. So I'm going to go ahead and start with an example. Okay, so in calculating what's called limits in calculus, we're going to use this example where imagine that you want to walk across a 60-foot wide room. Okay, and to do this, you must first walk halfway across the room, or 32 feet. Then to continue the walk, you're going to cover half of the remaining distance, which is 32 feet. Remaining distance of 32 feet, which is 16 feet. And then you're going to do it again and cover half of the remaining distance, which is half of 16, or 8 feet. Okay, so then what you'll see, therefore, is that we're going to sum every single one of those distances. So we start with 32, which was half the distance of 64, and then we're going to cover the next half, and then the following half, and the following half, and so on and so forth. And you could see that we continue this process. And if you continue this process, you'll start to realize that you'll never quite reach 64 feet, but you already know that the distance across the room is 64 feet. Okay, so then what this ultimately tells you is that you can add an infinite amount of numbers. So in this case, 32, 16, 8, 4, 2, 1/2, 1/4, 1/8, 1/16, 1/32. We can add them all together infinitely and still get a finite sum. Okay, so using this example, hopefully this helps you to understand the concept of limits. So while things can go on infinitely, they actually approach a specific number. Okay, so in this case, if you add all these numbers together, they actually reach 64 feet. Okay, so let's use the following example. Okay, so given the following quadratic function, f of x is equal to x squared plus 3x plus 5, what happens to the value of this function as x increases to infinity? Okay, so to demonstrate this, we're going to go to a spreadsheet. So we have the following spreadsheet, and we have this function, f of x is equal to x squared plus 3x plus 5. And I have all of the values of x's that we're going to enter into this function in column A. Okay, so let's go ahead and plug in this equation. We're going to say that this function is going to equal the value of x, in this case it's going to be 1, or cell A5, and we're going to square it, and then we're going to add 3 times that same cell, A5, and then we're going to add 5. Okay, so if we plug in a value of 1 for this function, we're going to get 9. Now, as we continue to increase this, let's say we add the value of 2, we're going to get 15, add the value of 3 in for x, the function is going to come out as 23, and if we add the value of x for 4, this function will come out as 33, and if we continue this process to 100,000, okay, we see that this number continues to increase infinitely, right? So as the value of x increases, the value of this function increases even more. Okay, so then we would say, therefore, that, and here's the notation that we will follow, that is the limit of the function x squared plus 3x plus 5 as x approaches infinity, this limit is actually equal to infinity, right? As I showed you in the spreadsheet, the higher the value of x, the higher the value of f of x. And as that continues to grow, so does the value of f of x. And so there is essentially no limit. And so we call that the limit of this function is equal to infinity. Okay, so let's go on to example number 2. So given the following function, f of x is equal to 6x minus 1 divided by 3x plus 2, what happens to the value of this function as x increases to infinity? Okay, so in other words, what is the limit of this function as x increases to infinity? Well, let's go to the spreadsheet and see what happens. All right, so I've got this function, 6x minus 1 divided by 3x plus 2. And then down column A, I have values of 10, 20, 30, going all the way up to 1 million. Okay, so let's see what happens. So we're going to say that this cell is equal to 6 times the value of x, in this case, cell A6 minus 1, and it's going to be divided by 3 times the value of A6, again, plus 2. Okay, so if I plug in a value of 10 for x, the function gives me 1.84. And if I put in a value of 20 for x, my function gives me 1.919. And then if I put in a value of 30 for x, I get 1.945. And if I continue this process as x increases, we see that it actually approaches 2. Okay, and so that actually makes sense, right? Because if we go back, we see that as x increases, right, this actually reduces itself so that what we're left with is just x over 3. I'm sorry, 6 divided by 3. And so the limit of this function, therefore, approaches the number 2. Okay? All right, so let's go ahead and move on to example 3. So given the following function, f of x is equal to 1 plus 1 over x raised to the x power, what happens to the value of this function as x increases to infinity? So in other words, what is the limit of this function, 1 plus 1 over x raised to the x power as x approaches infinity? Okay, so this function's a little trickier because if we do this intuitively, okay, I'm going to say off to the side here, if we to find the limit of 1 as x approaches infinity, we find that that is 1. Okay, so I'm just finding the limit of this component. If we find the limit of the second component inside the parentheses, we would say that the limit of 1 over x as x approaches infinity is equal to 0, because as this value gets bigger and bigger and bigger, this entire value gets smaller and smaller and smaller, and we say that it eventually becomes 0. Okay, it doesn't quite reach there, but it's approaching 0. So then we would say, therefore, that the limit of 1 plus 1 over x as x approaches infinity is equal to 1 plus 0, or just 1. Okay? But the function that we're looking at here is 1 plus 1 over x raised to the x power. And this is where things behave a little bit differently. And here's why. We know that 1 to the x power means that as x approaches infinity, it's still 1. However, with 1 over x raised to the x power, it doesn't go to 0. It's actually some value, okay? So what we would say is, therefore, there is some sort of conflict here when we focus in on 1 over x raised to the x power. So we can't say that the limit of 1 plus 1 over x as x approaches infinity is the same as the limit of 1 plus 1 over x raised to the x power as x approaches infinity. And so let's take a look at what this actually what this actually does as x approaches infinity. So let's go to the spreadsheet. All right, okay. So here we have the function 1 plus 1 over x, all raised to the x power. And I've got down column A, values of x from 10 to 20 to 30, all the way up to 1 million, okay? So let's go ahead and plug in this equation. This is going to equal 1 plus 1 divided by x, which is going to be cell A6, and that's going to be raised to the power of x, which is cell A6 again. And we see that that amount, when x is 10, the function is 2.59374246. So then let's see what happens when we put in a value of 20 for x. We get an f of x that increases to 2.65329. And if we continue this process all the way to 1 million, okay, we see that it actually approaches a number 2.71828, okay? And if you're not familiar with this number, this is actually a very popular number in the world of mathematics. And this number actually approaches a number in mathematics called E, okay? If you punch this value into the calculator, you will see that E is equivalent to 2.718281885, and it actually doesn't repeat itself. This is considered an irrational number. Okay, another irrational number that we are familiar with is the number pi, which is 3.1415, and it goes on and on and on forever. Okay, and so what we're discovering here is that this function 1 plus 1 over x, all raised to the x power, the limit of that as x approaches infinity is actually the number e. Okay, so how does this help us? Well, let's go back to our original example. In our original example, we talked about depositing $1,000, earning 100% interest, compounded continuously. And what we want to know is, what is our ending balance going to be? Okay, so now that we know that the limit of this function here, 1 plus 1 over x, is equal to the x power is equal to e, then to calculate this, we would say that the limit of $1,000 times that function is going to be 1,000 times e, or punching that into the calculator gives us $2,718.28. Okay, so then you might be wondering, well, where did this function come from? Okay, if you recall from the equation to solve compound interest, we said that the final balance is going to equal the principal times 1 plus the rate over the compound frequency raised to the compound frequency times years. Okay, so in this example, our principal amount is $1,000. Our rate is 100%, but it needs to be expressed in decimal, so our rate is just going to be 1. Okay, our compounding frequency we're going to call x, because it's going to be going to infinity, and then we're going to raise it to, and then our t is going to be 1 year. Okay, so if we were to plug this in to the formula, our balance is going to be 1,000 times 1 plus 1 over x to the nt. In this case, it'll just be x times 1, or just x power, okay? And you'll see that this equation or function is exactly the same as what we just calculated earlier. Okay, so hopefully that makes sense. So let's go on to the last example, example 5. And here's the question. If you deposited $1,000 this time and earned 2.3% interest, compounded continuously, what would your ending balance be to the nearest cents after 5 years? Okay, using 2.3% instead of 100% changes this limit expression to as follows. So this is going to be the limit of 1,000. This is the initial deposit of 1 plus, instead of 1 over x, it's going to be 0.023. This is 2.3% expressed in decimal over x to the x power as x approaches infinity. Okay? So to solve this problem, we would use a revised compound interest formula where the ending balance is going to equal the principal amount, so the initial deposit, times e, okay, to the RT power, okay, where R is the interest rate expressed as the decimal, and T is the number of years, okay? So then our balance is going to be B, ending balance is going to equal the principal, which is 1,000, times E, raised to the interest rate, which is 0.023, times 5 years. And if we were to plug that into the calculator, we would get an answer of $1,121.87. Okay, so this is how you calculate continuous compounding. Hopefully this made sense to you. If any of this was confusing, please go back to the beginning of the recording and listen to this again. Thank you.